Hello everybody, Selkan here and welcome to part 2 of our Sudoku solver using backtracking algorithm. If you want to check for the part 1 of the series, which is a discussion of the subject, you may do so by checking the timestamps in the description. What we have here is a board variable, which is the representation of the Sudoku board, where we have lists within a list and consisting of 9 rows with 9 columns to represent the Sudoku board, and inside we have the values from 1 to 9 to represent the partially filled cells in the board, and we also have the value of 0 to represent the empty cell in the board. Let's start off by defining a printboard function. This function actually isn't necessary, but it aids us visually to check for the board. And what it's actually going to do is it's going to take in the board as the parameter for which we are going to display to the console. And we're simply going to iterate through each row in the board and print each row. And there are actually several ways where you can improve this print statement. You may use list or string methods, but I just like to keep it as simple as it is. And let me just also print some dash lines here. And what this is going to do is it's going to print dash lines 27 times to create some nice division line at the end of the board. And let's just simply test it out, and the board being board 1, and so we see here the result of our function. Okay, and then before we proceed with our main backtracking algorithm, let's first define some helper functions. And again, these aren't really necessary, but it helps keep our code organized and short. And as part of our pseudocode, we actually need to find an empty cell in the board. So let's create a helper function for that. So let's call it find empty cell, and it's actually going to take in the board, and what we expect it to do is it's going to find the first 0, which is the empty cell in the board, and it's going to return us the coordinates of that empty cell, for which by coordinates what we mean is the rows in the column indices of that empty cell. And so let's lay out the logic inside this helper function. So the first one that we're going to do is we're actually going to iterate through or let's say all cells in the board, and we are going to check if the cell is empty, and at some point here we're gonna make some default return, and I'm gonna explain this in a moment. So let's start with by iterating through all the cells in the board. So we'll simply do that with this nested for loops for row in range 9. So we're basically looping through the indices from 0 to 8, and for column in range 9, looping through the column indices from 0 to 8. And then for each row and column indices, we're going to check if the cell on that specific coordinates or location is empty. And the way to do that is to call this statement here, row column equals value, and the way this our value is actually 0. And what this does is we have the two-dimensional list here, and by passing in the row index and the column index, we're actually getting the cell value here, and we're trying to check if it is 0, which represents the empty cell in the board. And if it is equal to 0, then that means that this cell is empty. And so we're going to return the coordinates for this empty cell, which is this row and column. So we're simply going to return the row and the column. And what this return statement does is it's actually returning the row in the column as a tuple with two elements. And it is also possible for that in iterating through all of the cells that we find no empty cell, and what that means is that the board is completely filled. And with that, we can say that there is no empty cell, and we just simply return none for that. So let's try and test this function. So we're gonna call the function find empty cell, and we're gonna pass in the board. But since this is not printing anything, we're actually returning the values, then we're gonna use the print statement and print the empty cell and pass in the board 1 as the argument and check if it works. Okay, so what we have here is the empty cell is at 0, 2, and that means that on row 0 and on column 2, which is this, so this is the first empty cell that it finds. Okay, and so we have a working helper function. And let's define another helper function here, for which we're going to check for the validity of the input, since along the way we're going to test a couple of values on a certain cell, then we're going to check for that validity of that case. So let's define a function called isValid, and what it's going to do is it's going to take in the board, and then it's also going to take in the row in the column, which is simply the location to where we're going to check for the validity, and also the value for which we are going to check if there is any duplicate of that value among the 3 rules of the key. And what we expect this to do is it's going to return as a boolean, and it's going to return as a true if the input values is valid, and it's going to return as a false if the input valid or input data here are invalid. And before we begin, let's lay out the logic within this helper function. So first, we're actually going to check for the row constraint, and then we're going to check for the column constraint, and lastly, we're going to check for the box constraint, and just like that. And also, we're also going to make some default return here. And let's start with the row constraint checking. And the way to do that is we're simply going to iterate through some indices in the range of 0 to 8. And then inside here, we're going to check if the value has any duplicates. So to do that, we can check value equals board and row, right. And what this does is at a certain row in the board, we're actually iterating through each of the element on that row, and for each element on that row, we're checking if the value has a duplicate, as a duplication, and if there is a duplication, that means that what it means is this is satisfied, and that means that we are going to return false, meaning that the input data row, the input data this is not valid. And we're also going to check for the column constraint, which is actually just quite similar with the row constraint, where we iterate through the indices from 0 to 8 and check if the value has any duplicates in the board. However, we are now going to iterate through each element on a specific column, and if there is any duplicate, then we're going to return false to signify that the input is invalid. And then we're going to check for the box constraint, and this can actually be further subdivided into two parts, where we find the box indices first, and then after finding the box indices, we're going to check for the for all 9 cells within the box. So we're simply going to use the formula that we had in our part 1 discussion. So we derive the box indices like so, where the box row index is simply the row integer division by 3, and the box column index is simply the column of the cell integer division by 3. And we're going to use this to locate all of the 9 or all of the cells within the box. And to do that, we're going to iterate through the OR in the range of 0 to 2, which is because the box is actually 3 by 3, so the indices within the box is from 0 to 2 for the row, and for the column just as the same. There are 0 to 2 indices in the box. And then we're going to derive the cell row index by using the formula that we had in the part 1 discussion video. And so the formula for this is box row index multiplied by 3 plus R, and the cell column index is just box column index multiplied by 3 plus R. And yeah, and then we're going to check if the value has a duplicate on that within that board, and we're simply going to indicate the cell row index and as well as the cell column index. And if there is any duplicate, then we're going to return false, and what it means is that our input is invalid. And lastly, here we have a default return, and what it means is if all of these cases above are satisfied, then that means that our input value is valid, so we're simply gonna return true. And let's try and test it out. So for this example, let's try to test if on this cell and try some input values. So let's call the function is valid, and we're going to pass in the board 1 as a parameter, the row is 0 and the column is 2, and let's try the value of 5, and we'll see here that the 5 is actually present in the row, so we expect this to return a false result. And again, inside this function we are not actually printing anything, but instead we are returning values. so we need to print the result here. And let's try and test it out, and we see that we get a false because the value of 5 is already in there. So let's try another value here. Among its column we have the 8, and so I should click so, and it returned false. And that's because the 8 is present in both the column and as well as for the box that it belongs to. Okay, and that seems to be working. Let's try the number 1, which is not within its row and not within its column and not within its box. Then we expect this to return true, which it does. Okay, so we now have a working helper function, and I think it's high time that we move on to our main backtracking algorithm. So let's define our backtracking algorithm. Let's call it get solutions by backtracking algorithm. So what this is going to do is it's actually going to take in the board as a parameter, and we're also going to take in the solutions as a parameter, which is actually going to be a list. And what we're going to do with the solutions is whenever we find a solution in our algorithm or along the way, we are going to update these solutions. And okay, and yeah, so before we do anything else, let's lay out the logic within this algorithm. And so from our pseudocode, these are the processes. So first we are going to locate the empty cell, and then we are going to check for the base case where there are no empty cell, or simply that the solution is found. And in the event that the solution there is an empty cell, then what we're going to do is we're gonna try values from 1 to 9 on an empty cell. And then for each trial value, what we're going to do is we're going to check for the validity of a value, and if it is valid, then we're going to perform these specific tasks, which is to create or update a new board, and then we're going to perform or solve with backtracking algorithm on the new board. And just for review, what this new board means is it has much lower or lesser number of empty cells. And then after doing this, then we actually have to revert the board back to its previous state to check for alternative solutions. And that's basically the layout or the tasks that we're going to do inside this algorithm. So let's start by locating the empty cell, and what we're going to do here is simply find an empty cell and use the helper function that we had developed. So find empty cell and pass in the board, which is simply this board parameter. And then if in the case that there is no empty cell, and what it means is the find empty cell returns the none value, then we're gonna add that to our solution. So what we're going to do is we're going to check if the empty cell is none, then we're going to have the solution, which is actually just the current board, or the current state of the board. However, in Python, this since the board is actually a list, then this may cause some problems, as whenever we change the board right here, when we create or update a board, then the solution will also be updated, since since lists are passed by reference, or they are in assignment, they are pointing to a certain memory in our certain part of our memory. So what I like to do here is instead just create an exact copy of the board, and I use the list comprehension for this. Cell for cell in row, and for row in board. Now you may do this the conventional way, where you have the nested for loop and then update the solution, but when we use the list comprehension, you can just simply move backwards here. So we'll start with for each row in the board, and what we're going to do is we're going to get each cell or each element in the row, and we're going to copy that cell into our new two-dimensional list, like so. And then finally, we're going to add that solution to our solutions. So what it's going to do is this solution will be appended to the solutions, and since our solutions here is a list, then everything in these solutions will be updated like so. And then lastly, we're going to make some return statement here, and this return statement doesn't really have anything meaningful to return, and what it simply does, it kinds of terminates, or it doesn't read the rest of the code below it, just like so. Okay, and then after that, we're going to try the values from 1 to 9 on an empty cell. So before anything, again, the empty cell here is actually a tuple. So what we want to do is we want to break down the tuple into different variables, like so. And in Python, this is called unpacking. So what the unpacking means is we're going to have this case where the empty cell is actually going to be a tuple, and as for example, let's have this. So we're going to have this case, for example, and what unpacking means is we have a tuple here with 2 elements and the variables here with 2 items, and what the unpacking does is it's going to assign this first element to the first variable and the second element to the second variable. So the row will be 0 and the column will be 2, like so. And that is what it does for the unpacking. And then now we are going to try the values from 1 to 9 on this empty cell. So we're going to iterate through the values in range from 1 to 9, and we're going to specify 10 because 10 is excluded, like so. And there we now iterate through the values from 1 to 9. And then what we're going to do here next is we're going to check for the validity of the value, and to do that we're simply going to check or call the isValid helper function that we have developed. And what the isValid function does is it's actually going to take in 4 parameters, starting with the board, and then also the row and the column, and which is the coordinates of the empty cell. And we're also going to pass in the value, and if this condition is satisfied, or rather this is value, and if this is satisfied, we're going to perform the rest of the operations here. So first we're going to create or update a new board, and to do that we're simply going to change the value on that empty cell. So again, this is the way to get the cell in a board, and initially this will be 0 since we are dealing with an empty cell here, and we're going to change that value from 0 into the value that we iterate through from 1 to 9 here. And then we're actually not going to use the equality sign but the assignment sign. Okay, and then once we have this new or updated board, then we're going to solve this new board and check for the solutions. So to do that, we're just simply going to solve this board just like how we solve this board. So we're simply going to call this recursive function and call solve, what's the name again? Yeah, get solutions. Get solutions by backtracking algorithm, which takes in two parameters, the board and the solutions. So let's pass in the board and also the solutions. And what the board here is this updated board, and what the solutions here is either so this is the solutions that we passed. Okay, and then we're going to revert back the board to its previous state. So we're going to do it like this, and its previous state is the empty state that it is. So we marked or updated it here, and then we're going to revert it back to its previous state like so. And with that ends the end of the algorithm, and let's try and test this algorithm out. So let me just remove this and have kind of the main function here. So here we display the initial board state, and then we perform backtracking algorithm, and also we're going to display all solutions. And yes, so in here, in performing the backtracking algorithm, we're actually going to define the solutions first, which is going to be an empty list. And what it's going to do is it's going to keep record of all of the solutions. And then we're going to get call the backtracking algorithm, passing the board, which is the board 1. And we're also going to pass in the solutions, which is this one. So we're going to pass in the solutions. And when this is run, the solutions will be updated, and since the solutions is a list, then anything that changes within this function, it's going to update the solutions as it is passed by reference, or it is changed directly in our memory. And then we're going to display the result of the solutions. So what we're going to do is we're going to iterate through each solution in the solutions, and we're going to print forward that solution to display each of the solution. And let's try and run this out. Give it a few moments. And it's quite taking a while. Okay, so there may be some issue in our code here. Oh, okay. So there isn't any issue. It was just taking a bit longer than expected. And yeah, so what it actually does is, let me just print this one up. So from our initial board state here, it actually returned all of the solutions that it can find, like so. And yeah, so you can check if these are actually valid. And let me just print here display status or whatever, and let's simply just print the number of solutions. So if number of solutions equals the len of solutions. And what this does is, again, we're dealing with an f string here, and what the f string does is we have this string and preceded by the f to signify that it's an f string, and wherever there is a curly brackets inside, then we're going to evaluate the variable or the value inside and convert it into a string. So for this case, we have the solutions. With the len function, it's going to take the number of the solutions, and so it's going to display the number of our solutions here, like so. So we can try that. And also you may also be concerned with the processing time of the this algorithm. So to display that, we actually have to import the time module, which is already built-in module in Python, so we don't need to install anything. And after calling that time, then we're simply going to define some clock start here, or rather this should be right here. So the clock start will be at the time.time, and I'm going to explain this in a moment. And we're also going to have here clock end for the time.time. Okay, so what this does is the time.time is actually going to get the number of seconds, and this one is also going to get the number of seconds. And just imagine that what the clock start means is we're actually hitting the button in our stopwatch, and then right here we're also hitting the button in our stopwatch to end the stopwatch. And whatever operations we have in between will be the difference in the time taken between the end and the start to get the processing time for this operation or this algorithm. And so we're simply going to print that, and let's call it processing time, and we're going to display it as it's going to be the clock end minus the clock start, and this will be the difference of the time and to represent the duration of the algorithm. And this will actually be in seconds, and so there are also some decimal places in it. So what I'd like to do here is to round off this difference with 2 decimal places and indicate here that this is in seconds. And also here, yeah, I think that's okay. So let me just try and run that one. and give it a few moments, and we're going to get the result in a few seconds. Okay, so let me just review the data here. Okay. And so there we have it. So we see that for this initial state of the board, there are actually 4 solutions, and the processing time is 60 seconds, which is about a minute. And yeah, and so there are also cases where you only want to have one solution, because actually you don't need that much solution to solve a Sudoku puzzle. And just think of it that you can save time if you do not solve for the rest of the solution. Okay, so initially here we have 60 seconds, then perhaps with one solution we can get the solution in like 15 seconds or whatever. So to do that, we can adjust our get solutions here, our algorithm, and perform another operation here, and this will be for if only a single solution is desired. And what we're going to do here is we're going to check if there is already a solutions, and what this means is in Python, when we have a solutions which is an empty list, then this is actually evaluated as false. But if you have a solutions with some values in it, like 5, 3, and so on, which is essentially just the board stored or as updated here in our solution, then this will be evaluated as true. So meaning that if this is empty, then that means that we haven't found a solution yet. So what we're going to do is we're just going to continue with the rest of our operations below. But if we already have a value inside, then what we're going to do is we're simply going to terminate or not read all of the rest out here. So yeah, and that simply solves our problem. So if we try to run this, then in a few moments we'll be getting the result. And just like so. So the number of solutions is 1, run with 21.63 seconds. And yeah, so just take in mind that with more empty cells in the board, then it will take much more time to process, but with more or with lesser empty cells in the board, then this will be much quicker. And I think that's it for this video.